Welcome. So last time we're starting about halfway through actually the laws of motion part 2. This is the applied part, and basically we did stuff where we worked out what our normal force was and what our frictional force was when we're on a slope, and we worked out various ways of doing that. And then we started looking at friction, and we decided there was a static friction and a kinetic friction, and we played with that for a while. And then we did numerical, plug and chug, and we did graphical, and we did ratio sections. We can do that on anything. That's just practicing the skills. And then we started talking about static friction, and we did some examples of that. And then we started talking about dynamics. And what I did was I got to this point, and I said, oh, there's a problem I want to do before I bring in friction on this, because we never did a smooth surface with a slope. So this really should have been, earlier, and we didn't do it. So, and because I didn't know how to put an extra page in, I kind of said ignore the question, and then we'll just use the space. So now I want to do this question, but the problem is because I saved it, I can't erase the ink. So I'm going to go to a clean page. And what I'd like, if you don't mind, is can somebody just read the question out to me, and I will, just 1 second on. Let me get my pen up and running. And I swear all these things with the stuff will get better. It's just learning how to do all the bits. So we'll go to a nice purple. So, oh, hold on. I want to go there. So what does the question say?
The masses are free to move. There is a 0.2 coefficient of kinetic friction.
Mu k equals 0.2. And then what else?
The block in the table, what is the tension in the strain once the system is released?
So, and what are the two masses?
The top one is 6 and the bottom, the top one is 2 and the bottom one's 6.
Okay.
8 minus 4.
So which one's 8?
That one.
That one, okay. Okay. So we have a friction full table, so let's just show it like that, basically. And, okay. I want to find the tension, so the first thing I do is I draw this thing as a stretch diagram, just same as normal. And I go back to my original diagram to get my actual numerical values. So this is going to be 80 newtons because it's an 8 kilogram hanging mass, mg. So that's going to be 80 newtons. And then this is going to be 8 kilograms. And here's my tension that is pulling back, reducing the acceleration of the 8 kilogram mass. And my tension, which is pulling the 2 kilogram mass forwards. Now, there is a backwards force of friction because it's a friction-filled interface. But I don't know its numerical value. So I need to figure out what its numerical value is, and I know that FF is equal to mu k times Fn. And if I look at this, I know that the downwards weight on that 2 kilogram mass is 20 newtons. And are you comfortable with, on a nice level surface, recognizing that the normal force, the Fn, would be 20 newtons? Are you comfortable with the fact that these two guys balance each other? Because there's no acceleration upwards or downwards. And yes, if I needed to prove it, I would then resolve my forces, in whatever direction could give me the answer. So, but most people can see it. If this is 20 downwards and that's 20 upwards, and it's a level surface, then it's fine. If it's on a slope, you have to do more work. Yeah. So then I can say, okay, well, in that case, then FF is equal to 0.2. That's my mu k times 20. So FF is going to equal 4 newtons. Agreed? 4 newtons. Yep. Now, the way I do it is I change my color of my pen so I don't get confused. I go to a nice red color, I think. So a nice red color. And I'm going to go and say, oh, let's pick this guy. So that's my system. and I say the sum of the forces on the 8 is equal to the mass of the 8 times the acceleration of the 8. So I look at my diagram and I say plus 8t added to, because I'm summing, minus t is equal to the mass, which is 8, times the acceleration on the 8. T is equal to 8t plus 8t minus 8 times the acceleration on the 8.
The tension is negative because it's going the opposite direction of the...
So look at your diagram. So I'm using the convention that positive is to the right and the negative is to the left, and this is the external force and it's pointing to the left, yeah? There's another tension there, but it's going to the right, but it's to do with this mass. Yeah, so I'm identifying this as a net, as a external force to this system. Yeah. And then the way I traditionally do it is I say, okay, let's find the acceleration. So let's do that just for the, I'm going to show you another way as well, but let's do that, find the acceleration. So I say, oh, let's change color pens. I'm going to go pen color, let's do a nice light blue. Did that come out? No, did not come out. Okay. Let's go to a nice ink color. I got to press harder. That's what I'm not doing. So then I go on, here's this light blue color. So that's my new system. And I say the sum of the forces on the system is equal to the mass of the system times the acceleration of the system. So now I look at this light blue box and I go plus 8t added to minus 4 is equal to 2 plus 8. So I know that I did it. I don't want to put down 10 because I won't recognize it as 2 plus 8. When I see 2 plus 8, I know I added my two masses together. I didn't forget. Times A of the system. So I say, okay, that's going to be 76 is equal to 10 A system. So A system is equal to 76 over 10, which equals plus 7.6 meters per second squared. And then the next little bit I want to do is some math. We'll just go to black. And I say, oh, if t is equal to plus 8t minus 8, the acceleration on the 8, and if I recognize that the acceleration of the system is equal to the acceleration on the 8, I can say, oh, t is equal to plus 8t minus, it's going to be 8 times 7.6, which equals 8t minus, well, let's just do it. Have I got a calculator on me? Oh, yes. In my pant pocket, I have my calculator. So this is, let's have a look. 8 times, well, let's do it. 8t minus bracket 8 times 7.6 bracket. Syntax error. What did I do wrong? Clear. 8t, use the wrong minus. 8t minus bracket 8 times 7.6. Close the bracket. I'm getting 19.2 on that. So t is equal to 19.2.
Why is this acceleration of the system the same as the acceleration of the 8?
So, is the acceleration of the front bumper of your car the same as the acceleration of the back bumper of your car?
Yes.
Why?
Because they're connected in the same direction.
They're connected together and they don't get closer together and they don't get further apart. Yeah? Yeah? So same for this. The length of string doesn't get shorter, doesn't get longer, so they're same. It's not obvious. It's not an obvious answer, but that's what it is. So that's going to be, say, take 20 away from 80 is 60. So this will be 60.8. Did I do that right?
Where'd you get 19.2?
No, the answer is 19.
Oh, the answer is 19.2. Yeah, sorry. I'm like, yes, the answer is 19.2. I'm glad there was a whole bunch of hesitation and then a correction there because I was lost. So 19.2. Put it in a box, put the units on. Cool. So it's the same old, same old. It's just we did a little bit of friction in the way. Yeah. Somebody asked me, could you not worry about acceleration because you have two tensions that are the same and you have an acceleration? You have potentially two equations, two unknowns. And it's just not my habit to do it that way. And I think it's not my habit to do it that way because I tend to think of things as the physicsy way. And simultaneous equations is a mathematical way, if you follow me, you know. But let me just erase this thing. I'm going to go, let's go here. Let's go pointer options. Let's go to ink color. Let's go back to black. And A8 is equal to A system. Let's put that there so that's still there. Let's get ourselves a little bit of space. And let's redo this problem, just doing it by saying, if I go back to red, then I say, yeah, the sum of the forces on the 8 is equal to the mass of the 8 times the acceleration of the 8. So that means that plus 8t added to minus t is equal to 8 times a. Let's just call it a. Well, a on the 8 just for consistency. So t is equal to 8t minus 8a8. And then let's say, okay, let's change our pen color. Let's go to a nice green. And then we go, there's my green. And let's just do the same thing now on the other mass. So the sum of the forces on the 2 is equal to the mass of the 2 times the acceleration of the 2. So I say plus t added to minus 4 is equal to 2 times a2. So t, well, I want to find t, but let's just hold on for a second. I'm going to have to do a little bit of finagling here. T is equal to 4 plus 2a2. Okay? I've got to do a little bit of finagling, so let's go here. Let's go to the good old black, and we'll do some math now. So actually what I'm going to do is I'm going to say, okay, two equations, two unknown. I want to find t in the end. So the first thing to recognize is that a of the 8 is equal to a of the 2 because, again, they're equidistant apart along the length of string. The string doesn't get shorter or longer, so they just track each other. So then I can say, okay, in the first equation, let's rearrange for a. So I'm going to say 8a is equal to 80 minus t. So a is equal to 10 minus t over 8. And then we're going to substitute that. So that's from there. And then we substitute that into here. And we come down here. And we go t is equal to 4 minus 2 times 10 minus t over 8, which equals 4 minus 20 minus minus makes plus t over 4. So that means that, take that t over 4 to the other side, 3 over 4t is equal to minus, I don't like this, I've got a minus sign already, minus 16. I'm going to live with it for a minute and see what I get. So that would give me that T is equal to, let's have a look, 4 16s are 64 divided by 3. That's not right. I got a mistake somewhere, so let's have a look. It doesn't matter. I got a mistake somewhere. It's not the right answer, is it? So let's see if we can spot my mistake. This first expression, plus 8 plus minus T is equal to 8 times that. So T, took that to the other side, is equal to 8T minus 8 times A.
It can still be negative T.
On this side?
Yeah.
Let's have a look. I took that to the other side. No, I took that to the other side, it became positive. I took the 8A to the other side, it became negative. So, no, that's positive. What about this side, though, the new one? So I said plus T added to minus 4 is equal to 2 times A. So T is equal to 4 plus 2 times A. So that looks right. Oh, dear. So then 8A is equal to 8T minus T. So A is equal to 10 minus T over 8. So T is equal to 4 plus 2. Ah, there's my mistake, isn't it? Rather than minus. Isn't that a plus?
Yeah.
Bad teacher. So that goes there.
But you've also done like,
Oh, just let me think it through. So I said 4 plus 2A, and my A, we said was 10 minus T over 8. So this is 4 plus 20 minus T over 4. Because 2 times that is T over 4. And yeah, okay, I'm feeling a bit more comfortable now. So scribble, 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 scribble. So then what do we have? We have T plus T over 4 is equal to 24. Which gives us that 5 over 4T is equal to 24. I'm feeling good about this, I think. Maybe not so good. So T is equal to 24 times 4 over 5. I'm feeling good about this. Which equals what? 19.2. Yes, happiness. Yeah. So although I show you it sort of like, let's find A now, you know, you could have just used simultaneous equations. It's a bit more mathematical. You know, I tend to think of the physics approach to things, but it's just as legitimate. But if you don't practice it, then if I ask you a question of what is the acceleration, then you know you've not practiced it. So I still like my way. You know. So questions about that? Yep.
could you have also solved for A with the 2?
Oh yeah, no, you can do. You got two equally important equations. I can isolate A in the red one and then substitute into the green one, or I can isolate A in the green one and substitute into the red one. I'll still get the same answer. Yeah. Yeah. Cool. Okay. So not bad. Okay. So, oh man, this is a slope. Just you've got the skills. Just work through it. So this 3 kilogram block has an acceleration of 1.5 meters per second squared, pointing down the slope. So I'm telling you the acceleration is in that direction. The coefficient of kinetic friction, mu k. So remember what I say, don't rely on my diagram. That's 20. Little block, big arrows. 30 newtons. Fn. which is the direction that the FF will tend to point?
Right.
It's going to be up and to the right. FF is going to be up and to the right. And what do we know? We know mu, is it moving? Yes. Mu k is equal to, what's that number? Oh, it wants you to find that. It doesn't know what mu k is. And my acceleration is equal to 1.5 meters per second squared. I'm going to write down because it's important. Down slope. So what's going to fiction? I am going to put, this is my shorthand. I put my masses as numerical values inside the blocks. I put my forces typically as pulling forces, even if it's pushing force. I'll move it to the other side as a pulling force. I use the arrows coming away from the block rather than the arrows going into the block. That's just my habit. I get the right direction. I do it correctly, but I tend to have my forces going away from the block. My accelerations, I need to show my acceleration. And so what I do is I'll often go to a different color and I'll show my acceleration not directly in line with the block. My velocities, my accelerations are like over to the side. It's just a habit. So this is my acceleration. Okay. Many step problem. First step, try and solve it. So mu k. What equation do I know includes mu k? FF is equal to mu k times Fn. So, okay, no big deal. At mu k is equal to FF over Fn. Okay, this is no big deal. All I have to do is find, what should we start? Let's start with Fn. Find Fn using, okay, let's have a look. I don't want to deal with this FF because I don't know it. And I certainly don't want to deal with the acceleration. Well, no, I do know it. Actually, I do know it. I don't have to find it. But I don't want to deal with it. So what I say is, oh, let's draw a line. Let's draw this line perpendicular to the thing I want to get rid of, which is, sorry, I'm doing this green. The thing I want to get rid of, which is I want to find Fn, so I want to draw my line like that. Yeah. The sum of the forces perpendicular to slope equals, what do they equal perpendicular to the slope? Is it 0 or ma? This object is accelerating, so is it 0 or ma? Why is it 0 when there's an acceleration? What's constant? Sorry?
It's an equilibrium.
It's an equilibrium, but it's accelerating. So, pardon? No? Why? It is in equilibrium perpendicular to the slope.
It's the axis.
It's the axis. So what we've got to do is we've got to start linking accelerations. So we've got to start linking Newton's laws with a direction. When we say this object is in equilibrium, we're really been sloppy with our language. This object is in equilibrium along this axis. And it might be in equilibrium along that axis, which means it's in equilibrium along any axis. But equilibrium is along axes. It's not just in general. Now, in colloquial speech, we say that's not accelerating in any direction. It's in equilibrium. But really what we mean is it's in equilibrium along any axis I choose. If it is accelerating, going to make my microphone go crazy. If it is accelerating, yes, it's accelerating vertically. So it's not in equilibrium vertically. But it didn't accelerate towards you guys. So it is in equilibrium horizontally. So we've got to use the equations along an axis. So I was kind of deliberately throwing you off there and saying, but it's accelerating. But I wasn't saying it's accelerating down the slope. I was saying it's accelerating. So remember to link these equations to specific axes. So the sum of the forces perpendicular to the slope is perpendicular to the acceleration. So that's going to be 0 because it is in equilibrium in that direction. So people, the gut feeling was right. It's just solidifying why the gut feeling is right. And so we say, okay, looking in that direction, I go, well, okay, I'm going to go dash, dash, dash. And if that's 20, and I drew a decent diagram, so I can immediately see that that's 20 degrees. I don't need to mess with that. So then I say, well, this is going to be 30 cosine 20. And I've got to decide on my signs on this. I'm going to call that a negative direction, which means that's a positive Fn. We have this vector up here is a positive Fn. No component on that because it's actually in the same line as the green axis. So I say, okay, plus Fn added to minus 30 cosine 20 is equal to 0. So Fn is equal to 30 cosine 20. And what is that? Let's do a numerical value for that. So what is 30 cosine 20? 28.19? 28.19. Thanks. Now, let's have a look. Let's go to pointer options. Let's go to a new color. Let's go to a nice red. That'll stand out. I don't want to deal with Fn. I want to find FF. Here's the tip. If ever you have an acceleration, make sure you resolve in line with that acceleration. Otherwise, you have to take components. So it's my tip is I would always be sure to resolve in this direction. Find FF using the sum of the forces parallel to the slope is equal to MA. It is accelerating. There is that acceleration. I've got to take it into account. So I go, okay, dash, 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 arrow in that direction. That is going to be 30 sine 20. Got my FF in that direction. But I've also got my A. Let's make sure we put our A down so we don't forget it. Got my A.
Was that what slope? Parallel slope?
Yep, parallel slope. So I say, again, let's make that positive and make that negative. Doesn't matter, just pick one or the other, but make sure you pick one. Plus FF added to minus 30 sine 20 is equal to, the mass is 3, and the acceleration I was given, it's 1.5, isn't it?
I'm sorry, I can't see where the 30 sine 20 is coming from.
Basically, that's 20 degrees. Yep.
Oh, okay.
So it's the opposite over the hypotenuse. I got a mistake. Can you see what I'd made for my mistake? Look at your signs.
Yeah, FS positive.
Sorry?
FF should be positive.
It is. It says positive, yeah.
Accelerations, positive, negative.
That's right. It's a negative. Can you see how, just, you know, I just slipped this in. 1.5 meters per second pointing down the slope. That's giving you a direction. But it's tempting to write down, oh, it's just 1.5. And then you got the wrong direction and your answer's wrong. So can you see how if you're verbal and you're going to an equation and you don't have a diagram, you might miss that. But with a diagram, especially if you're careful with the diagram, then you won't miss that, because you got an arrow on your diagram pointing down the slope, and as I do the sum, you know, I put a positive at one end, I put a negative at the other end. I looked and said that's pointing towards the positive. I looked and said that's pointing towards the negative. Then I looked at my acceleration and said that's pointing towards the negative. It reduces my chances of making that slip. And for me, it is a slip because I am doing the diagram. If you don't do a diagram, it's not really a slip. It's like you're going to make that mistake quite often because you're not using a diagram. You're not going to see it very often. So just be careful about that. So then I say, well, FF is equal to minus 4.5 plus 30 sine 20. FF is equal to, let's have a look. Oh, sorry about that. Oh, I'm trying to use my phone as a calculator, which is never going to work for me. So it's going to be 30 times sine 20, enter, and then I'm going to subtract from that minus 4.5, and I'm getting 5.76. I got a positive 5.76, and that just simply says whatever direction you assumed is right. So then I say, oh, we can just go back to doing math now, and I'm going to say, oh, then mu k is equal to ff over fn, which equals 5.76 over 28.19, which equals, pardon? 0.2, yeah. Okay, 0.2. What are the units for this? No units. Good. Don't get caught with that. So what do you think? It's just Newton's laws. They're straightforward. They're really simple equations. But it's using Newton's laws along mindful directions. And it's just Newton's first law and Newton's second law. This is not harder than if it was stood still, although most people will find it harder when they begin. Because yeah, some of the forces equals 0, some of the forces equals ma. I'm giving you a. You know m. It's just, does it equal a 0 or another number? It's the same equation. It's the same difficulty. But it's that level of, you know, uncomfortable with a bit more uncomfortable with a bit more uncomfortable. And the rules are, you know, I really mean this from the heart. A good diagram is your best friend. If your sense is I can slide by without doing good diagrams, it will bite you. And one of the major criticisms that we hear for people at higher level is that people can't draw diagrams. They complain. I was at a teacher training thing recently with engineers, and that's what's their big complaint. People can't draw a free body diagram. This is basically a free body diagram. People can't draw one. And it's like they've got to be able to draw one because our things are more complicated. So it's really good to embrace this. It's like having a corked baseball bat, you know? If you do a better diagram, you'll hit more home runs. You know, think of it as cheating. It's like it really helps. If you don't do the diagram, it shoots you in the foot. So, and when you get used to doing the diagrams, life gets simpler. Get yourself some different colored pens. You know, I'm using different colors because it helps me get the problem right when I'm doing it in front of you, when I'm nervous. So just get yourself some different coloured pens and get used to drawing it up. And you'll just fall into a pattern and life will get easier. Just help yourself because life will get easier. It's not that this is hard. It's that it's uncomfortable and it's coming like a train. You know, this is not about intelligence. This is about training. So just go to the gym, you know, and do 25 of these, you know. By the way, brings me to an issue, which is, so supposing that you do all the homework that I set and then you still need practice, where would you go next? And so you could go to the back of the chapter questions, and there's some credit to that. They are not unreasonable questions. They're just long. They tend to be linguistically hard rather than physically hard, although there are some that are just they're harder. There's no question about that. That's where you're going to go eventually. It's just that I think if you get those for homework to begin with, it's going to be over-facing, you know. People remember those questions. We got really good memory for complex things once we've solved them. And so anyway, when you do a very complicated problem and you see something like, again, you remember it. Oh, I remember this. Whereas these questions, because they're more fundamental in a way, they test your fundamental thinking. So what would I do? I would go to the bookstore and I would buy something like a AP Physics book to get you up and going. Not necessarily AP Physics C. I'd look at AP Physics B, but C's fine. And I wouldn't necessarily look at the APs divided into two bits. There's one bit which is very much like this. That's the first part. And the second bit is very much like the back of the chapter problems, which is the second part. And in the AP, you do a bit of both. You do more of the first than of the second in terms of time, I think. But you do. And I would get one of those and just drill myself on it and just go through it. There's a lot of those books, SAT prep and stuff like that. They sometimes have stuff that's very useful to us. Okay, questions on that? Everybody okay? This last bit is apparent weight, and it's kind of interesting. It's intriguing. But it involves some understanding, some deeper understanding of how some of the apparatuses work. So we have a scale. So I went fishing and I grabbed hold of a force meter, sometimes called a Newton meter, sometimes called a spring balance. And amazingly, I caught a fish. So I weigh, well, depends on what my scale is set to. We're not going to talk about pounds. I could have a scale that's calibrated in newtons, in which case it's a force scale. That same spring can be calibrated in mass, kilograms, in which case it's a mass scale. Let me ask you a question. If I took it to the moon, would the force scale still be calibrated correctly?
Because you have to adjust for gravity.
Oh, this is, oh, I love this. This is like, so check you on, so we're going to come down here, we're going to go Newton, so spring balance. You know the stretchy thing? Yeah. On moon. Newton, scale, okay. That's A. Kilogram, scale, okay. That's B. Both, okay. That's C. Neither. Okay, that's D. Vote. Let's see. Very good.
So when
Vote.
they change, or you're asking, okay, as in
You have an object, and you use this scale on Earth, and you can look at its mass using the mass scale, or you can look at its weight using the weight scale. You go to the moon. Which one of those scales will be wrong? Which one of those scales will give you the wrong answer on the moon?
All right, so those are the ones that are right.
So the ones at the right, if you think the Newton scale is okay, say yes. If you think it still reads right in the mass scale, kilogram scale, then say that. If you think both of them are okay, say C, and if you think neither one of them, they're both messed up on the moon, then say D. Sorry?
There's a little bit of perspective about this question.
No, it's actually, no, it's either be right or wrong. Same fish, well, fish will explode. Same rock, same scale. You can talk about it, because you are. You can talk about it.
We're assuming a scale that presses downwards.
This thing that hangs like in the lab, that little hook thing with a
Right, so that's
spring inside,
down.
it hangs down, yeah. This is interesting. So I'm going to stop you in 10 seconds. 9, 8, 7. Good. I'm very pleased. Any more people? Come on, have a go. Come on. It's too late. Okay. Let's have a look. I'm really curious. Ooh. So I can see, the people on the right-hand side will be generalists. The people on the left-hand side, it's very split, isn't it? So we've got to ask ourselves, how does the spring balance work? What happens physically? You have a spring,
Gravity pulls the object down.
and what happens to the spring?
It decompresses.
It
It
stretches, doesn't it? And so the length of the spring depends upon the force it feels. Yes?
Yes.
Yes? The force it feels. The length of the spring depends upon the force it feels. So if you're in a place with a lot of gravity, it will feel a big force, and it will be right. And if you're in a place with a little bit of gravity, it will feel a small force, which is right. Yeah? So vote again. Okay.
So what's the question again? Are we saying that the measurement on the scale is correct, or are we saying that they're different?
I'm saying the measurement on the scale is correct.
Oh.
So if the Newton scale is measuring correctly, if it's okay, press A, on the moon. If the mass scale is measuring correctly, on the moon, do B. If you think both of them are measuring correctly, on the moon, press C. If you think neither of them is measuring correctly, on the moon, press D. So I'm not saying the same numerical value. I'm saying, is it measuring correctly? On the moon. I'm going to stop you at 1 minute, 15 seconds. What do you think? Man. This is very interesting. We use these things all the time. Not on the moon. We can't afford it, but... Whoa!
It's even worse.
So, okay. I would say that if I look at the blue bit and the yellow bit, then the fair number of people are saying that the Newton scale is okay on the moon. I mean, the yellow is saying both of them are okay. So they're saying, well, yeah, the Newton's okay. And the blue people are saying, well, the Newton's okay. But only the Newton's okay. So there's a fair number of people saying the Newton scale is okay. And if you think about it, if the length of the string depends upon the force, and there's a small force on Earth, so you get a big number, and there's a small force on the moon, so you get a little number, there's no problem. It's just you're going to get a big number on the Earth and a smaller number on the moon. It's still been pulled. It's still working. So the Newton scale is okay. The problem is with a kilogram scale. Because to get that string spring to work. It's all about force. And you get that grams scale by converting from a force to a mass. You say W, the force, equals mg. Oh, I measure W and I know what g is, so I can convert this into an m scale. That's what they're doing. They're assuming a g to convert a Newton scale into an m scale. Yes.
So do you mean that the spring previously comes having the gravity of Earth in it?
The spring's just a spring. All it knows is it's been pulled.
The scale?
But for the mass scale, for the kilogram scale or the gram scale, they assume it's on the Earth. And so they multiply, they basically take the newtons, they divide it by 10, and they call it kilograms. That's how they do that thing.
So that's Earth gravity.
So then when you go to the moon, you got a different G, so it doesn't work. So if you said blue, yay! If you said yellow, half yay. If you said red, no, it's the other way around. And if you said purple, you're kind of like, you probably have a lot of friends. you're probably a very, like me, you're more, easygoing. Yeah, okay, I'll take a bit of both. I'm going to stop there. I'm going to take a bit of a break. Let me have a quick look. Maybe I can just finish this. Yes, I'm going to go for it. Okay. So that's the game we're playing. What we're doing is we're going to use a spring balance. It holds up a spring, holds up a fish, and the fish basically gives a reading. Now, what do you notice when you get into an elevator and you press the up button and it starts moving? What do you feel? You feel it like a push down on yourself, don't you? And that is because there's an acceleration. No longer is the sum of the forces equals 0, which is when you're standing still or you're moving at a constant speed. But for that instant, when you're increasing your speed, the sum of the forces equals ma. And at the top, what do you feel when you get to the top of the elevator? When it gets to your floor and you stop, what do you feel? Inertia kind of wants you to keep on going, doesn't it? And so you feel this lightness. And on the way down, if you press the scale on the way down, then you feel like you're left behind. So you feel a lightness. Then when you get to the bottom, you feel, ooh, kind of like. When I first came to the States, I went to the World Trade Center, the old World Trade Center, and they have express elevators to take you to the top, and those things fly. And so you go from 0 to a high speed in a really short amount of time. And you could feel, I'd never quite felt that shuddering. It's not like the elevator here, which has very little acceleration. These things, huge acceleration. Okay, so what would happen to my spring balance, to my mass, to my force scale in an elevator? Well, it will be affected by the acceleration. And so the reading will change. My fish will seem to be heavier when I start going up, and it will be lighter when I get to my floor. But it's the same fish. Its mass, sorry, I keep saying mass. Its weight cannot change. It's a fish. It's on the earth. The gravity doesn't change. It's the acceleration that's messing with the reading. And so this is an exercise in dealing with that. And so let's do one. We say a 4 kilogram object hangs from a force gauge. So here's my 4 kilograms. And here's my tension in my string. And what happens is the meter reads the tension. The meter's reading the tension in the little wire that you pull on. So, okay. And so in equilibrium, that's what I have. I have my 40 down. I have my tension pulling up. I have my tension pulling down on the string. And there's my hand holding this thing up. Yeah? So a 4 kilogram object from a force gauge, hangs from a force gauge while traveling in an elevator that is moving upwards and speeding up. If I'm moving upwards and speeding up, which direction is my velocity in? Which direction is my acceleration in? Because you speed up when your velocity and your acceleration point in the same direction. Its acceleration is 3 meters per second squared. 3 meters per second squared. What is the apparent weight? Apparent weight equals t. That's the bit that you might not immediately recognize. It's the reading of the scale while you are accelerating. Apparent weight is reading of scale while accelerating. And at all times, your weight is equal to t. I should really say weight is equal to t. So apparent Wt is equal to the tension while accel. This might seem like, oh man, how are we going to take this into account? Ask yourself, is this in equilibrium vertically or horizontally? Vertically. Is this mass in equilibrium vertically? No. Sum of the forces vertical equal ma. The sum of my forces vertical plus t added to minus 40 is equal to my mass times my acceleration. Which direction is my acceleration in? Upwards, so positive. And what's its size?
40?
What's the size of the acceleration?
3.
So t minus 40 is equal to 12. T is equal to 12 plus 40, which equals 52 newtons. So when I'm in the elevator going upwards, my 40 newton fish now apparently weighs 52 newtons. That's when I take the picture of it. Okay, just like 52 newton fish. Boom. I just increased my weight.
What if it's going big?
So, good question.
Not a fish, but anything new.
What if it's not doing that? I'm going to put this on stop. Cool. So we voted, and most people are saying A. And let's just check on that. So basically, I draw my system. I have my 4 kilogram, means 40 newtons. It has been pulled upward by the tension in the little string, and that tension on the string is also pulling downwards on my scale. So my weight is equal to my tension. That's the thing I gotta kind of recognize. And my apparent weight is equal to my tension while accelerating. I am accelerating in this case. It says traveling in an elevator that's moving upwards, so my V is upwards, while slowing down, so my acceleration is downwards. So rather than plus 3 meters per second squared, it's minus 3 meters per second squared. I say this is not in equilibrium vertically, so the sum of the forces vertically is equal to ma. I look at my block and I look at the external forces. I have plus t added to minus 40. Look at the mass is equal to 4 times a, and a in this case is minus 3. So rearranging, t is equal to 40 minus 12. T is equal to 28 newtons. A. And so it appears to have less weight than it had when you were stood on the ground, when you are slowing down at the end of your upwards journey. Okay? Cool. Let's pause there. Let's stop there.